Okay, 3.4, position, velocity, and acceleration. Velocity is just a measure of how quickly position is changing. Acceleration is just a measure of how quickly velocity is changing. So this stems directly into derivatives. First off, I'm going to give you a graph of a position function just so we can wrap our heads around what a position function is. So a position function gives the position of an object at any given time. In this particular case, we have this particular function shows the distance a rabbit hops into a tunnel. So the rabbit goes into a tunnel and at some point turns around and starts coming out of the tunnel. This is measuring the distance in feet in which the rabbit is in the tunnel, and that's the time in seconds at any point in time that the rabbit is hopping. All right. I would strongly encourage you to try these 3 questions on your own. Being able to do this on your own is going to help you out with it. Pause the video, see if you can answer these 3, and then I'll go over them. All right. How far into the tunnel is a rabbit after 20 seconds? Well, 20 seconds is right here. Goes up to there. That's roughly, let's just say 6 feet, maybe about 5 feet, 6 feet. So I'm just looking for an estimate here, but this is just measuring distance after a certain amount of time. So it's just like you reading any other graph. So let's call that 6 feet. Does a rabbit ever turn around, and when? The answer is yes, right about there. Let's call that 37.5 seconds. You could have said 37 or 38, but somewhere around there. I'm going to say 37.5 seconds. So I can tell it was turning around because its distance into the tunnel was getting more and more and more. It's going deeper, deeper, and deeper into the tunnel until right there I had a maximum depth of 20 feet into the tunnel. And then its distance started decreasing. Right there, it's only 10 feet into the tunnel. So it went to 20 feet in the tunnel and then back down to just 10 feet. So it must have turned around right at that point where I reached a maximum. Question 3. The slope seems to be fairly consistent for time 0 less than t less than 20. Give an estimate for the slope at this point within this range. What would be a good label for this number? Well, we had guessed that at 20 seconds, we were about 6 feet into the tunnel. And it looks like we started at 0, 0. So it looks like we got a rise of 6 and a run of 20. So that slope would be a slope of about 6 over 20, which I could reduce down to 3/10 if I prefer. So I've got a slope of 3 over 10. A label for this is rise over run, right? I'm going to write up here slope equals rise over run. That rise wasn't just a 6, it was 6 with, I'm not sure if you can see that because my video, I'm going to move this. There we go. That 6 wasn't just a 6, it was a measure of distance. It was 6 feet. That run of 20 wasn't just a 20, it was a time. It was 20 seconds. So when I measured that 6 out of 20, that was 6 feet for every 20 seconds, which would reduce down to 3 feet per second. That is a speed. The rate of change in position is speed or velocity. That rabbit during this section right here was traveling about 3/10 of a foot per second. Big important note. Velocity is a derivative of a position function. Since I was talking about finding slope here, and when I found slope of a position, I got a measurement of velocity. Well, derivatives are a measurement of slope. So velocity is a derivative of a position function. If I've got some function y and it's a position function, it tells me the position of any object after a certain amount of seconds, then y prime, the derivative, is going to be a velocity function. It'll tell me the speed of that object at any given time. Let's continue to explore that a bit. I've got the same function here, So it's still a position function, gives me the position of the rabbit after a certain amount of seconds. But now I'm going to start asking questions about the velocity, about when is the velocity of the rabbit 0? Well, again, velocity is the derivative of position, so it's just going to be the slope. So that's asking the same question as when is the slope of that function 0? If I look up here, it's right about there. Let's call that 37.5 seconds again. At that point in time, the rabbit's velocity is 0. That should make sense. We'll talk about it in a minute. Is the velocity of the rabbit ever negative? Well, again, velocity would be the derivative. So it's basically asking, is the slope ever negative? And the answer is going to be, again, yes. If so, where? Well, during this entire section here, my slope is a downward slope. So from 37.5 seconds all the way to 50 seconds. From 37.5 seconds all the way to 50 seconds. So this should make sense. My velocity was positive. I had a positive slope during that entire section there. Then I had a negative velocity afterward, right? So positive velocity, then a negative velocity, and right in the middle, I had a velocity of 0. That's because this rabbit was hopping into the tunnel. So right, a positive velocity moving into the tunnel. It stopped right there to turn around, right? And when you stop, your velocity is going to be 0. That's why I had a slope of 0. And it started going backwards. Going backwards would be a negative velocity. So this was going forward, right? Positive slope. I was going backward, negative slope. And right there, it was stopped, right as it was changing from a forward movement to a backward movement. That's the same as velocity. Forward velocity would be a positive velocity. Backward velocity would be a negative velocity. When you have a velocity of 0, you are stopped. All right. Question 3 speaks to the difference between something called speed and velocity. A lot of times we interchange those two as meaning the same thing. They're not quite the same thing. Velocity is a speed in a given direction, right? So a forward velocity would be a positive velocity. A backward velocity would be a negative velocity. Speed, however, is just speed, right? If I'm in a car and I'm going 20 miles per hour forward, that would be a positive 20 velocity. If I was going 5 miles per hour backward, that would be a velocity of negative 5. But if I talked about speed, I say I'm going 20 miles an hour forward, or I'm going 5 miles an hour backward, but I'd never say I'm going negative 5 miles per hour. That's different. Speed is just always a given. It's the speed you're going without a positive or negative component. It's just a number, right? I'm going 12 miles per hour, right? In that direction, in your point. If you're talking about velocity, then it actually is a given direction. Like if that's the direction, I'm going 12 miles an hour that way, then I've got a velocity of 12. But if I was going backwards 5 miles an hour, I've got a velocity of negative 5 instead of a speed of negative 5. Speeds can't be negative. Speeds are just the speed you're going. So that leads to this. Speed is the absolute value of velocity. In other words, if velocity equals 12 feet per second, then so does speed. But if velocity equals a negative 8 feet per second, meaning you're going 8 feet per second in reverse, your speed is still 8 feet per second, is just 8 feet per second, right? It's the absolute value. We don't give a speed a positive or negative component. It's just the positive version, right? So speed is just the same thing as velocity. The difference is velocity can be positive or negative, indicating your direction. All right, almost done. Velocity measures the rate of change of an object's position. Acceleration measures the rate of change of an object's velocity. In other words, acceleration says how quickly your velocity is changing. So in calculus terms, acceleration is the derivative of a velocity function. because that'll measure how quickly velocity is changing. If you like it, some people write it like this. They like just putting it in their head. They say if y is a position function, then y prime is velocity. We talked about it before. And then the next derivative, the second derivative, that'll measure acceleration. Velocity is a derivative, acceleration is the derivative of velocity. Or you could think of it as the 1/2 second derivative of the position function. All right, let's talk about some acceleration questions for a minute. Be careful of what graph you're looking at. This is not a position function anymore. This is a velocity function. I can tell it's a velocity function because it's measuring velocity over some given time, right? Velocity function gives me velocity. So be careful of what the questions are asking you. I'm gonna pause here again and see if you can answer these questions. Actually, you pause it. I'm gonna keep talking. All right, so when is the rabbit moving forward? Well, it'd be moving forward when it has a positive velocity, right? Well, here's 0. A positive velocity is anything more than 0. So I would have a positive velocity during this entire section here, right? Those are all positive numbers. So I've got a positive number velocity all the way up until right there, which looks like that 37.5. Same as before, right? Over here, when I had a position function, I was moving forward all the way to 37.5. But now instead of seeing a position function, I'm seeing the exact same function as a velocity function, but the information is still going to be the same, right? I'm still moving forward during that entire time. It's just now I see it as an actual velocity, a positive velocity, positive values, and over there's a negative velocity or negative values right there. That's when my velocity is 0, right? So I'm going to highlight this, all that area. That's a positive velocity because it's above the x-axis. Right here, that's when my velocity equals 0. And then down here, those are all negative velocities because they're all negative values, right? So when is the rabbit moving forward? Well, when the velocity is positive. So from 0 to 37.5 seconds. When's he moving backward? Well, that's when I have a negative velocity from that 37.5 seconds on up to 50 seconds. When, if ever, is a rabbit not moving? Well, not moving means you have a velocity of 0. That happens right there when you're changing from a positive velocity to a negative velocity. So exactly at time t equals to 37.5. Question 3, though, starts asking about the acceleration. So acceleration is how quickly velocity is changing. Since we had just mentioned one page up that acceleration is a derivative of velocity, when I ask about acceleration and I have a velocity function, it's really asking about the slope of that function. So when it says, when is the acceleration positive? That's the same thing as asking, when is the slope of this thing positive? Well, I can see I've got a positive slope right there, right? It's going upward there. So the acceleration is going to be positive from t equals 20 seconds to, looks like 30, from 20 to 30. Oh, and I see another spot, also here, right? Positive velocity there. It's going upward, positive slope there. So let's add that. Union, that looks like it's starting at 45 seconds all the way to 50. When is the acceleration negative? Well, that's when you have a negative slope, because slope is, this would be the derivative of velocity, derivative of measured slope, right? So I've got a negative slope all during that section. In this case, starting at 30 and all the way up until 45, right? That whole section there, from 30 seconds all the way to 45 seconds. Sometimes at this point, students ask about, like, what about that first part right here? What's the velocity there? Well, velocity measures slope. What's your slope there? 0, right? That horizontal line's got a slope of 0. That's not a positive number. That's not a negative number either. 0 is uniquely the one number, the one real number that's neither positive nor negative. It's right in between. All right. We should have a short conversation about speeding up versus slowing down, because that can sometimes confuse people. So speeding up is when you are going faster and faster and faster. Slowing down is when you are getting closer and closer to a speed of 0, right? You are going fast, but you're slowing down. Again, it'd probably be good to pause this and try to see if you can answer this on your own. All right, so speeding up or slowing down. Velocity and acceleration are both positive. I'm going to do this in green. If you had a positive velocity, that means you're going in the forward direction. If your acceleration was positive, that means you're speeding up in the forward direction. You're going to be going faster and faster and faster. You're going in the forward direction and you're accelerating in the forward direction. That's going to speed you up. However, the next one, if velocity is positive but acceleration is negative, that means you had a positive velocity. You're going in the forward direction, but you were accelerating in the negative direction. That's the opposite way. You're accelerating in the backwards direction, which means you were going forward, but your acceleration is negative, it's backward. It's going to slow you down. Velocity and acceleration are both negative. All right, well, if velocity was negative, that means you're going backwards. If acceleration is negative, that means you're accelerating in the backwards direction. That means you're going to go faster and faster in that direction. It's a rate of change. You're already going a negative speed, right, velocity, and you're accelerating even more negative. Your acceleration is negative. That's going to speed you up. It's going to push you backwards even faster. Velocity is negative and acceleration is positive. That means if you are going backwards in reverse, but accelerating in the positive direction, that means your speed, instead of being negative, whatever, negative 10, is going to slow down and get closer and closer to 0 because your speed, your acceleration is in the positive. Your speed, your velocity is going from a negative 10 to a negative 8 to a negative 5 to a negative 4, right? Going faster and faster and faster in the positive direction. That one is slowing down because your speed would be getting closer and closer and closer to 0. All right. One last example question and we are done. It says a ball is thrown upward with a velocity of 80 feet per second. Then its height after t seconds is this equation. H of t equals 80t minus 16t squared. Be careful. A lot of times people see that word velocity and they're like, oh, this must be a velocity function. It is not. That's a position function. How can I tell? Because it gave me height after a certain amount of seconds. Giving me height would be giving me position. How high up in the air is it? So that is a position function. H of t, I'm just going to rewrite it here, equals 80t minus 16t squared. And I'm going to write position out right after that. I know it's a position function because it's giving me the height in feet. Height is a position. I'm asked to find h prime of t. Well, that should be easy at this point. Derivative of 80t would just be 80. Minus derivative of 16t squared, that'll be 32t. And I'm asked to find h double prime. Well, derivative of 80 is 0, right? Derivative of a constant is 0, so that's gone. Derivative of negative 32t is just negative 32. Again, if h was a position function, then this one would measure velocity, and this one would measure acceleration. All right. 2. So same stuff up here. So it hasn't changed at all. Problem 2. Why should it make sense that h double prime of t is a negative constant? All right. So I gotta think and remember what this thing is measuring for it to make sense. So the ball was thrown upward with a certain velocity. H double prime is acceleration. It's how that speed is changing. When you throw the ball upward, the speed is going to be going pretty fast up. Eventually it's going to slow down and then come down because of gravity. Gravity is going to be pulling that ball downwards. This is the acceleration due to gravity. It makes sense that that acceleration should be negative because the acceleration due to gravity pulls the ball downward. It doesn't push the ball upward, right? It pulls it downward. That's a negative direction. Up is a positive direction, down is a negative direction, and gravity pulls downward at a constant acceleration. In fact, it pulls downward at exactly 32 feet per second squared. That's why it's a negative 32. All right. So why should it make sense that h double prime is a negative constant? Because acceleration due to gravity is constant. I'm going to say n downward slash negative. All right. 3, what is the velocity of the ball at exactly t equals 3 seconds? All right, so I had my 3 functions. I'm going to rewrite them here. All right, this question's asking me the velocity of the ball. Well, first one measured position, second one measured velocity, third one measured acceleration. I'm asking a question about velocity. I'm just going to use that equation. I'm going to find h prime of 3, the velocity at exactly 3 seconds. This is measured in this would be 80 minus 32 times 3. 80 minus 32 times 3 is negative 16. In other words, I can tell that after 3 seconds, the ball that's been thrown in the air, it's already falling back down towards Earth. How can I tell? Because its velocity is negative. It's coming back downward. In fact, I can tell specifically how fast that is. That is negative 16 feet per second. I know it's negative 16 feet per second. I know that's the label because the height was measured in seconds, right? If I did a quick graph here, I'm going to see if I can do a quick graph here. If I had a graph where something was measured in feet and the x-axis was measured in seconds, and I was finding slope, right? Well, that's feet per second. So a rise in feet or run in seconds, it's going downward. So it's negative feet per second. All right. Last is what is the maximum height of the ball? Again, I'm going to write those 3 equations. We're going to need them here. All right. So again, that first equation was a measurement of position. The derivative would be a measure of velocity. And then the next derivative would be a measure of acceleration. All right, this question is asking the maximum height of the ball. If it's asking about height, I am definitely going to want to use a position function because position's going to give me height, right? How high up in the air the ball is. Unfortunately, I don't know what time to plug in there, right? I don't know when it reaches a maximum height. So to find that, I'm actually going to use this velocity function. I'm going to use a velocity function because I know when the ball goes up into the air, it's going to have a positive velocity. When it comes back down and down, it's going to have a negative velocity. But right there at its peak, its velocity is going to be 0, right? When you throw a ball up, it's got a positive velocity as it rises up. Right when it reaches the peak of its height, it's going to briefly stop. And then it's going to have a negative velocity coming down. Now that stop is instantaneous, right? It's going up, stops and comes down, but I can't go up and then start coming down without stopping somewhere at the top. So I am going to reach the maximum height when my velocity is 0. So I don't know when that time is yet, but I know whenever it happens, it's going to be when my velocity is 0. So what I'm going to do is I'm first going to set my velocity equation equal to 0. I'm going to write 80 minus 32t equals 0, because I want to find out how much time it takes for that velocity to become a velocity of 0. That'll be when I'm right at the peak of my thrown ball. Well, that's a pretty simple equation to solve. 80 would equal 32t. I'm going to get t by itself. I'll put t on the left this time. Divide both sides by 32. 80 divided by 32 is 2.5. T is measure of time, so that's 2.5 seconds. Now, that's when my velocity is 0. That's the amount of seconds that pass for me to reach the tip, the very top of the peak of that ball, right? That's where I reach the maximum height, or sorry, that's when I reach the maximum height. To find out what that maximum height is, just plug that time into your position function. Now that I know when I reach the maximum height, I can use this position function and find the height at 2.5 seconds. It's going to be 80 times 2.5 minus 16 times 2.5 squared. That reaches 100 feet high. That's a high thrown ball. It's going to reach a height of 100 feet. And then it's going to fall back down. All right. See me during my office hour if you have questions. Give those a try. See you later.